morning students. This is lecture number 24. Its title is Integer Programming. The outline of this lecture is as follows. First we will define what is an integer programming problem and a mixed integer programming problem. Then we will learn two methods. One is the branch and bound method and the second is the Gomory's cutting plane method. This we will illustrate with the help of examples and finally some exercise. So, let us begin. First of all, let us define an integer programming problem. As you know that a linear programming problem has already been defined in the previous lectures. The only difference in the general linear programming problem and the integer programming problem is that in the case of integer programming problems, the decision variables should be restricted to be integers. So, in the last line here, this is the definition of integer programming problem. In the last line here I have written that all xi's should be integers. So, that is the most important thing that has to be noted in this particular definition. Now, coming to the mixed integer programming problem, this means that there is a linear programming problem which has let us say n number of variables, and out of those n variables let us say t of them are integers and the remaining ones are non-integers. So, here you can see xi's are integers only for I is equal to 1 to up to t, where t is less than n, and the remaining ones are not necessarily integers. Of course, the order of the variables can be changed. For example, there is a situation where let us say variable number 1 and variable number 5, they are integers, and the remaining ones let us say 2, 3, 4, they are not integers. So, that reordering of the variables is possible. Now, let us take a simple example to illustrate the two methods that we are going to study in this lecture. The first one is that a farmer has to plant trees of two kinds A and B in a land 4400 meters square in area. Each A tree requires at least 25 meters square and B tree requires at least 40 meters squares of land. The annual water requirement of A is 30 units and of B is 50 units per tree, while at most 3300 units of water is available. The return per tree from A tree is expected to be 1.5 times as much as from B tree. What should be the number of trees of each kind so that the expected return is maximized? Now, let us model this as follows. Let x1 be the number of trees of the type A and similarly x2 be the number of trees of the type B. Obviously, it is common sense to understand that x1 and x2 should be greater than or equal to 0 and they should be integers, because you cannot grow let us say 2.5 trees. You can either grow 2 trees or you can grow 5 trees or 3 trees. So, this once we have understood the significance of integer programming problems, now let us take a simple mathematical example where we have a two variable problem which says that maximize z is equal to 3x1 plus 4x2 subject to 2x1 plus 4x2 less than or equal to 13, minus 2x1 plus x2 is less than or equal to 2, 2x1 plus 2x2 greater than or equal to 1, 6x1 minus 4x2 less than or equal to 15, x1 and x2 are greater than or equal to 0 and x1 and x2 are integers. Now, we can use the graphical method to see what the feasible domain looks like. So, here on the horizontal axis we have the x axis that is and on the second axis, the vertical axis, we have the second variable. Now, as you can see that this solution to this problem, if you just consider that x1 and x2 are not integers, I mean if they are real numbers, then the solution lies on this point indicated over here, the point number C. And but our problem that has been given is that x1 and x2 should be integers. So, in the next slide I have written the solution of an LP if you consider that x1 and x2 are not integers, just as an ordinary LP, and in this case the feasible domain is A, B, C, D, E, F, as is indicated over here, A, B, C, D, E, F. This is our feasible region. And the optimum solution is at the point C given by 7/2, 3/2, and the objective function value is 33/2. Now, suppose we do the rounding off, that is we round off 7/2 and 3/2 to the nearest integer, then we have the following 4 feasible points. They are 3, 1, 4, 1, 4, 2 and 3, 2. See, because 7/2 is 3.5 and 3/2 is 1.5. So, we will look at 3.5, 3.5 lies between 3 and 4, and similarly 1.5 lies between 1 and 2. So, based on this we can look at the 4 feasible points as 3, 1, 4, 1, 4, 2 and 3, 2 as the feasible points. But wait, what do you find? You find that the last 3 of them are not feasible. 4, 1, 4, 2 and 3, 2, they are not feasible because they are going out of the feasible region. It can be seen over here in this diagram. So, the only feasible solution obtained by rounding off is 3, 1, and which makes the objective function value z is equal to 13. So, this is the only solution that is remaining. Now, let us look at the solution of the integer linear programming. The same problem if you impose that x1 and x2 should be integers. In this case, the set of feasible solutions are the points in the polygon A, B, C, D, E, F whose coordinates are integers, that is the discrete points. So, these are all discrete points, and if you look at the feasible region diagram, these are the points that are the ones that are shown in the green dots. These are the discrete points in the feasible region which satisfy the integer requirements of our integer linear programming problem. So, this means that we have these points, and among these points the objective function value z is maximum at the point 2, 2 where z is equal to 14. So, this means the true solution to the integer programming problem gives us the solution at 2, 2 with objective function value 14, and the rounding off gave us the solution at 3, 1 which is z is equal to 13. So, this means that the process of rounding off has given us a wrong answer, and that is the reason why we need to devise methods to solve a integer programming problem. Now, the question is the feasible region of an integer linear programming convex or not? And the answer is no, because the convex hull of this non-convex feasible region is, which is shown in green. Every vertex of this convex polygon is a feasible solution of the integer linear programming problem. Remember, the definition of a convex set is that the convex linear combination of all points should also belong to the set, then only it is said to be a convex set. But since it is a discrete set of points, therefore, it does not satisfy the definition of a convex sets, and hence the feasible region of an integer linear programming problem is not convex. The optimal solution of this problem is 2, 2 which is optimum solution of the given integer linear programming problem. Thus, the optimum solution of an integer linear programming problem is the same as the optimum solution of the linear programming problem, whose objective function is the same as that of the integer linear programming problem, but whose constraints are such that the convex set of feasible solution turns out to be the convex hull of the set of the feasible solutions of the integer linear programming problem. So, let us look at the first method. It is called the branch and bound method. So, we will take a 2 variable problem, maximize 3x1 plus 2x2 subject to x1 less than or equal to 2, x2 less than or equal to 2 and x1 plus x2 less than equal to 3.5, x1 and x2 are integers and both greater than or equal to 0. Let us call this linear programming problem as LP0 and let us try to look at what the feasible region looks like. So, the graphical solution of the LP0 is shown here in this figure, and you can see that the feasible region is indicated in the pink region. The vertices of this region are shown here in this table, and you find that the optimum solution is given at B, which is given by 2 comma 1.5. Now, this we have just plotted thinking that there is no integer restriction, but since we find that the solution B given by 2 comma 1.5 is not an integer solution, 1.5 is not integer. So, therefore, we need to do something, and what we will do is that we will impose this as a restriction. So, since x2 is not an integer, we remove the strip given by 1 is less than x2 is less than 2. Please note the strict inequality from the feasible region by imposing two constraints, that is x2 should be less than or equal to 1 and x2 should be greater than or equal to 2. Therefore, since both these conditions cannot be imposed in the same LP, therefore, we will impose these two conditions separately, which will give rise to two different LPs. So, we have two new LPs, we will call them as LP01 and LP02. So, LP01 is obtained from LP0 by imposing the constraint x2 is less than or equal to 1, which is shown on the left side, and similarly LP02 is obtained from LP0 by imposing the condition that x2 should be greater than or equal to 2. So, now we have got two different LPs. Let us now try to solve them. So, the graphical solution of LP01 looks like this, as is shown here in this graph. Apart from the original LP0 constraints, we have an additional constraint, and this is what it looks like, and the solution to this LP01 gives us the point B, which is given by 2 comma 1, and fortunately 2 comma 1 is a integer solution. So, we are very happy with this because this is what we were looking for. Now, coming to the other LP, that is the LP02, we find that the feasible region is nothing but this line segment as is shown here in the diagram. So, it is given by the line segment AB, and the solution is B, which is given by 1.5 comma 2. But again we find that 1.5 is not integer. So, therefore, we will repeat the same process what we had done for the LP0, that is we will remove a strip since LP02 x2 is x1 is non-integer. So, we will remove this strip 1 is less than x1 is less than 2 from the feasible region by imposing two constraints, x1 is less than equal to 1 and x1 is greater than or equal to 2, which again will give rise to two more LPs, and we will call them as LP 0 to 1 and LP 0 to 2. And this is what it looks like. LP 0 to 1 has the original constraints as well as the constraints of LP 0 2 as well as the additional constraint that x1 is less than equal to 1, and similarly LP 0 to 2 has the additional constraint that x1 is greater than or equal to 2 apart from the original constraints. Now coming to the solution of LP 0 to 1, this is what the feasible region looks like, that is, it is the line segment as shown in the diagram, and the solution to this problem is given by B 1 comma 2, and as you know that 1 comma 2 is a integer solution, and this is what we were looking for. So now we will look at the LP 0 to 2, and we find that this is a infeasible problem. The feasible region does not exist. So the entire thing we can represent in this diagram. Starting from LP 0, we have written down the nodes and the constraints that were imposed to get the various LPs, and we find that the last node, that is LP 0 to 2, is infeasible, and the LP 0 to 1 is having the solution 1 comma 2 with objective function 7, and the LP 0 1 is having a solution 2 comma 1 and objective function is 8. So since it was a maximization problem, therefore the solution to the problem is LP 0 1, which is giving 2 comma 1 as the solution. So I hope everybody has followed how this procedure is to be implemented. Now coming to a LPP with more than two variables, the new LPPs at the lower levels can be solved by using the procedure of the sensitivity analysis, that is what happens if another additional constraint is added. The mixed integer linear programming problems, caution has to be made to apply the removing feasible region strategy only for those variables which are restricted to be integers and not to the other ones. So now let us take another example, minimize f given by 3x4 plus 4x5 plus 5x6 subject to these conditions. Here we have again the structure of the bifurcations of the new LPs that we get, and this is the solution shown in this diagram. Now the second method that we will study is called the Gomory's cutting plane method, and let us take this example to understand it. So suppose we have to maximize twice x1 plus x2 subject to 2x1 plus 5x2 less than equal to 17 and 3x1 plus 2x2 less than or equal to 10. Both variables are non-negative and integral. Now the optimum solution to this problem is shown here in this table. You know how to solve it, thinking that it is just non-integral, and the solution to the problem is given by x1 is equal to 10 by 3 and x3 is equal to 31 by 3, which is non-integral. So therefore since we want integral solution, therefore we need to impose certain mechanism. So x1 corresponds to the constraint x1 plus 2 by 3 x2 plus 1 by 3 x4 is equal to 10 by 3, which is shown here in the table. Here you are. So x1 plus 2 by 3 x2 plus 1 by 3 x4 is equal to 10 by 3. We will split each of the fractional coefficients and the constants as sum of integer and positive fractions between 0 and 1. that is, for example, 2 by 3. This 2 by 3 we can break into the integer part and the non-integer part. So, since it is less than 1 already, so we have broken it into 0 plus 2 by 3. Suppose it was more than 1, then you remove the separate out the integer part and remove out the non-integral part, both separately. So, you have x 1 plus 0 plus 2 by 3 x 2, and similarly 1 by 3, this 1 by 3 is broken into 0 plus 1 by 3, and the same thing has to be done for the right hand side constant. 10 by 3 is broken into 3 plus 1 by 3. So, here this is greater than 1, 10 by 3 is greater than 1. So, you can separate out the integer part, which is 3, and the non-integer part as 1 by 3 separately. Now, once you do this, then you can transform all the integer things on the right hand side. This x 1 goes to the right hand side, and the right hand side becomes 3 minus x 1. So, once you have written this equation in this fashion, where on the left hand side we have the non-integral parts and on the right hand side we have the integral parts, but the left hand side should be greater than or equal to 0, because all the variables xi's in a LP are supposed to be greater than or equal to 0. So, therefore, if you put this left hand side greater than or equal to 0, you get a resulting condition, that is 2 x 2 plus x 4 is greater than or equal to 1. So, we have obtained a cut, this is called as a cut. This cut is corresponding to the x 1 variable. So, I hope you have followed how a cut is evolved corresponding to x 1 variable. So, now the new LP becomes the following. Objective function is same, twice x 1 plus x 2, subject to 11 by 3 x 2 plus x 3 minus 2 by 3 x 4 is equal to 31 by 3, x 1 plus 2 by 3 x 2 plus 1 by 3 x 4 plus which is equal to 10 by 3, and this third condition is the cut that we have obtained in the previous slide. All variables should be integers and non-negative. So, adding the surplus variable x 5 and then the artificial variable x 6 and applying the two phase method, we can get the optimum solution, or alternatively you can use the sensitivity analysis where you can add an additional constraint so that you can get the new solution. So, the table 2 gives you the result, and the table 2, from the table 2 you find that the new cut corresponding to x 2 is the following: x 4 plus x 5 is greater than or equal to 1. This has to be obtained in the same way which as I have explained for the x 1 variable. So, this additional constraint has to be imposed. So, now the new LP becomes the following. So, this is again x 4 plus x 5 is greater than or equal to 1. This constraint has been added corresponding to the cut that we have obtained. So, all variables again are supposed to be integers and non-negative. And the resulting table, the solution that is shown here in this table, table 3, and we repeat this with x 1 is equal to 8 by 3, and finally the solution is x 1 is equal to 3, x 2 is equal to 0 with objective function f is equal to 6. So, in this way we have learned the two methods to solve the integer programming problem. So, this is an exercise for you to try out whether you have understood the method or not. Solve the following programming problem, integer linear programming problem, by the branch and bound method, and also repeat with the Gomory's cutting plane method. Maximize 11 x 1 plus 21 x 2 subject to 4 x 1 plus 7 x 2 plus x 3 is equal to 13. All x 1 and x 2 and x 3 should be non-negative integers. The answer to this problem is 3, 0, 1 with objective function value as 33. So, with this we come to an end of this lecture on integer programming problem, where we have learnt the two methods to solve an integer programming problem. Thank you.